we can get information about the position of an object and its location from a velocity versus time graph without going to the trouble of fully reconstructing its position versus time graph. The conclusions I'm going to draw here are very general, so let's start with just sort of an arbitrary velocity versus time curve. So let's just make some curve. Shape doesn't matter too much. Something like that. All right, so here we've got an object that clearly starts with a positive velocity, slows down a little, but it's moving still in the positive direction, then speeds up in the positive direction, reaches a maximum speed, moving positively this whole time, then slows down a bit, but is still moving in the positive direction, moves at a constant speed for a while, then slows down a bit more, but never quite comes to rest. All right, so he's moving in the positive direction this whole time. I would like to know from this moment, which I'll call T1, to say this moment, T2, between these two times, how far did this object go? What was its change in position? Can we figure that out just from looking at the velocity versus time curve? Let's see. At time 1, we can note that the velocity was right there. We'll call it V1. And at time 2, the velocity of the object was this value up here, this higher value. We'll call it V2. Okay, so all right, we know its velocity at the beginning of that interval, we know its velocity at the end, and that means that it has some average velocity over this time interval. It's hard to tell what the average velocity is from this curve because we don't know the exact shape of this curve. It's just some random thing I drew. But we know that its average velocity has to be somewhere between this starting velocity and this ending one. It looks like I'm probably somewhere right in between. So let's just take a guess and say our average velocity. We know there is an average. It's probably somewhere in between, probably right about there. Okay, can we use that average velocity to help us out? Well, let's go back to the definition of average velocity. The average velocity over a time interval can be found from the change in position over the change in time. All right, if we rearrange that equation a little bit, let's multiply both sides by the time interval. Multiply both sides by delta t. Well, delta t cancels delta t over here, and that lets us rewrite this relationship as delta x equals the average velocity, so your displacement can be found if you take the average velocity over that interval times the time interval. Okay, so if we knew this average velocity, we could just multiply by the change in time here, and that would tell us the displacement. I'm going to draw a box. This box has length delta t here, and the width of this box from top to bottom is the average velocity. Okay, so it's kind of a strange box. It's got a length in terms of seconds and a width in terms of meters per second, but that's okay. I'm saying the top of this box is at the average velocity, which we know is, somewhere between the starting and ending velocities. Okay, so average velocity there, that is like the length of this box. And our time interval, that's like the width of this box. Okay, so if I take length times width, that gives us the area. Of the box. So the area of this box would seem to be equal to our displacement. If we can figure out the area of the box, we know our displacement between these two moments. Okay, well, let's look at this scale here. If we assume it's 1 second per box here and 1 meter per second per box here, our length, the average, looks like 1, 2, 3, 4 meters per second. 4 meters per second here. And our time interval is 4 seconds. 1, 2, 3, 4. So our length times width is 4 meters per second times 4 seconds. Seconds cancels seconds. 4 meters times 4 gives us 16 meters. That's the area of this box. 16 meters, which is also then the displacement from here to here. That means that from this time to this time, from here to here, this object traveled, well, its change in position was 16 meters. Exactly the same as the area of that box. Okay, I'm going to look at another area on this graph. I'm looking at this total area underneath the curve from T1 to T2. Okay, that pink area there. And I'm about to make a claim. This claim is I can't prove it, not without some calculus, but I'm claiming that the area under the curve from T1 to T2 is exactly equal to the area of this box made from the average velocity and the time interval. I'm saying that these two areas are the same. Do you believe me? Could you look at it by eye and kind of convince yourself that if you cut off this little chunk up here, it would fit into this piece right here, and this box area would be the same as that pink area? In fact, it's something so important in calculus that's called the fundamental theorem of calculus, a very lofty title. Can't prove it today. You'll have to take my word for it. I'm making a claim. So if my claim is true, I'm saying that the area under the curve is the same as the area of the box, which is equal to the displacement between time 1 and time 2. So I'm saying that this area is exactly equal to 16 meters. This is one of our key concepts when we're graphing quantities in kinematics. On a velocity versus time graph, the area between the curve and the v equals 0 axis between two events, T1 and T2, this area is exactly equal to the displacement between those two events. Furthermore, an area above the v equals 0 axis, so an area up here, that represents a positive displacement because the velocity is positive this whole time, so the object is moving in the positive x direction. But an area below the v equals 0 axis represents a negative displacement. During this time, the object is moving in the negative x direction, so its displacement has to be negative. That's a positive area. Under the axis here is a negative area. But distance traveled, remember, it's always positive. This is the change in the reading on your odometer while you're moving. So for distance traveled, any change in your position is a positive move. So you're moving here and you're moving here. So this counts as a positive distance traveled. This also counts as a positive distance traveled. Let's look at an example. All right, here we have a velocity versus time curve for some object. I would like to know how far this object has moved over some different time intervals. Let's say from time equals 0 to 6 seconds. So from here to here, how far has the object moved? Well, we can use our key concept here to say that the displacement between two events is equal to the area under the curve between those two events. So let's figure out the area. Let's break up this into some sections. There's this rectangle here. That's easy to find the area of. We can get the area of a rectangle. And then there's this triangle right here. We can get the area of that triangle. And that'll be the whole area under the curve from 0 to 6 seconds. All right, well, this is 4 seconds here times 2 meters per second, which tells us that this has an area of 4 times 2, 8 meters. Okay, so the object goes 8 meters from here to here. Then from 4 seconds to 6 seconds, we've got this triangle here. You know, the area of a triangle, 1/2 base times height. So that's 2 seconds times 2 seconds is 4 divided by 2. That's an area of 2 meters there. So from 0 to 6 seconds, the displacement is these 8 meters plus these 2 meters. The object changed position by 10 meters in the positive direction. Its distance traveled is also 8 meters plus 2 meters. It was moving in the positive direction that whole time, so it moved a distance of 10 meters. Okay, what about from 0 to 9 seconds? From here all the way out to here. All right, well, we already know these two areas. We'll also need the area of that little triangle there and the area of this rectangle right there. Okay, well, this is 1 times 1 divided by 2 because it's a triangle. That right there is an area of -1. Oh, no. 1 times 1 divided by 2 is -1/2. So that's -0.5 meters right there. Negative because it's below the 0 axis. It's a negative velocity. The object was moving in the negative x direction during this time. This rectangle, that's 2 seconds times 1 meter per second. So that's an area of -2 meters. Okay, so let's add them all up. So our displacement from 0 to 9 seconds, 8 meters plus those 2 meters minus 1/2 meter, went backwards 1/2 meter, then went backwards 2 meters. So our total displacement was 7.5 meters in the positive direction. Total distance traveled, he went 8 meters, then he went 2 meters, then he went backwards another 1/2 meter, but we counted positively. Then he went backwards another 2 meters, so that is 12.5 meters is his distance traveled. 10, 12.5, right. Okay, one more, 2 to 8 seconds. So from this time here to this time right here, what's our displacement from this moment to this moment? All right, we've got to add up these displacements again. First, we'll need this box here. That's 2 by 2 is 4. 4 meters right there, plus these 2 meters. Then minus this 1/2 meter, went 1/2 meter backwards. And then here's 6, 7, 8. We just got to go from here to here, so that's just this box right there, which is minus 1 meter backwards. Okay, so that's 6 minus 1 is 5, minus 1/2 is 4.5 meters. And then our distance traveled, we just add them all up positively. We count all those displacements as positive. So that's 6, 7.5. Alrighty, I've got some for you. If I can find them. Uh-oh. Ah. There we go. Okay, so I want you to pause the video and work out the displacement of this object and its distance traveled during these time intervals. From 6 to 13 seconds, from 11 to 17 seconds, and from 0 to 19 seconds. Pause now. Ready for the answers? Here we go. Let me point out a few things. The area of that little triangle right there, that is a -1 meters. Area of this triangle right here, ooh, bad triangle. That's a positive 3 meters. Then for this shape, we've got a rectangle topped with a triangle. So that rectangle is area of 6 meters, triangle area of 1 meter, so you would need to add both of these up. Then we've got this rectangle that is -2 meters, that triangle, that's a -1 meter. This triangle, that's a +1 meter. So this triangle and this triangle would cancel each other out if you're moving from here to here. And then lastly, we've got that little square, +1 meter, and that little triangle, +0.5 meters.